platform engineers face a tough challenge. Developers, on one hand, know what they need, but they don't understand complex infrastructure. On the other hand, platform engineers understand infrastructure, or should understand, but they struggle to anticipate every developer requirement. So what's the result? Well, the result is often that we get internal developer platforms that miss the mark and platforms that require endless iterations to make them useful. But hear me out. What if there is a third collaborator that could bridge this gap? AI, for example, has vast technical knowledge, but doesn't know your company's specific rules and constraints. However, when you combine developer intent, platform engineering expertise, and AI's technical knowledge, well, something powerful emerges. I'm about to show you a working system that demonstrates this three-way collaboration. We'll watch developers express their needs in natural language. We'll see AI translating those into deployments using platform engineering building blocks. And then I will talk or reveal the architecture that makes all that possible. How does that sound? We'll take a quick break for me to introduce you to Blacksmith, the sponsor of this video. Here's the story. No matter which AI agent you use, you will eventually push code to GitHub, and that will trigger GitHub Actions that will build binaries, run tests, make a release, and do whatever else workflows normally do. That's where Blacksmith comes in. It makes your GitHub Actions much faster and cheaper at the same time. And all you have to do is change a single line in your workflows. A single line for faster and cheaper workflows that make them run on high-performance CPUs instead of GitHub's old servers. On top of that, they made significant software optimizations that allow you to get much faster Docker builds and faster collocated cache. Unlike some other solutions you might hear about here in this channel, this one is truly a no-brainer. Sign up, add that single line to your workflows, and enjoy faster GitHub Actions workflows at much lower price. Big thanks to Blacksmith for sponsoring this video, and now let's go back to the main subject. Almost everyone is using AI in some capacity or another these days, right? Models are incredibly capable at understanding context, generating code, and solving complex problems. But what makes them truly powerful is when they're enhanced with agents that can gather information and use tools to take action in the real world. Then we have MCPs that extend agents with specialized tools that go far beyond what's available through traditional command line interface. But that's also where this capability intersects with a fundamental problem in platform engineering. Internal developer platforms are typically built by platform engineers who make assumptions about what developers actually need. Even in the best case scenario, those platform engineers end up spending tremendous amount of time treating developers as customers, approaching their platform like a startup that's still trying to figure out what the market needs. They typically go through, when they're good, they go through this classic startup cycle, trying to understand what developers want, then building something, then failing to deliver what developers really need, then trying again, then iterating endlessly until they eventually stumble onto something truly useful. It's the exact same process startups go through when searching for market fit. But here's the harsh reality. Most platform engineers simply do not know what developers need, and they're unlikely to ever figure it out. Now, to be clear, this isn't a criticism of their technical skills or dedication. It's just the nature of the problem. The gap between what platform engineers think developers need and what developers actually need is often enormous and very difficult to bridge. And even if platform engineers somehow figure out what developers need today, those needs are constantly changing. What was essential yesterday might be relevant tomorrow as new technologies emerge and development practices evolve, right? So, who actually knows what developers need? Developers themselves. Isn't it obvious? They understand their workflows, their pain points, and exactly what would make their lives easier. But here's the catch. developers typically don't have deep experience with databases and clusters and cloud providers and networking and all the infrastructure complexity that those applications depend on. They might not have the time to learn all those infrastructure details, and even if they do, it's often too much for any one person to master. The infrastructure landscape is vast and constantly evolving. Now, you, as a platform engineer or a database administrator or Kubernetes expert or any other infrastructure specialist, do know those details, right? But who else has this knowledge? You wonder? I wonder? We wonder? AI. Large language models have been trained on vast amounts of technical documentation and real-world examples and production experiences and countless discussions about what works and what doesn't across different environments. So why not leverage that extensive knowledge? The challenge isn't that AI lacks technical or production knowledge. The challenge is that AI does not know the specific practices in your company. It might not know that you always use a specific region in Google Cloud, and which VPC must be used in AWS, which database service can be used in Azure, which ingress class and service mesh should be used in Kubernetes, and countless other company-specific decisions. These organizational constructs, those preferences and standards are unique to your environment, and they are not part of any training data. And that's where the solution becomes clear. Instead of platform engineers trying to guess what developers need, AI can work directly with developers to understand their requirements. AI has the general technical knowledge, and you know what the company rules and best practices are. That's a three-way collaboration. You let AI do what it knows how to do, and you, as a platform engineer, focus on creating guidance, restrictions, governance, and all the guardrails that define how things should work in your organization. If those constraints are provided to the AI, it can provide services the developers actually need while still, at the same time, ensuring those services meet your company's rules and standards. Now, here's the thing. The implementation is straightforward. You, as a platform engineer, should provide the building blocks. Those could be Kubernetes CRDs and controllers, policies, governance, rules, system prompts, and all the foundational components that define your platform's capabilities and constraints. Once those building blocks are in place, AI agents can do the rest. They can take a developer's intention, understand what needs to be built, and assemble the right combination of your building blocks to create exactly what the developer needs. Now, this approach might sound horrible or great in theory, but does it actually work in practice? Let me show you a project I've been working on in action. First, we'll see it solve simulated deployment problems, and then I will explain how it actually implements those concepts. Sounds good? Let's see this concept in action. I want to walk you through creating and deploying applications using .ai or DevOps AI Toolkit MCP to demonstrate. I want to demonstrate how AI can work directly with developers while still respecting all those platform engineering constraints we discussed. Okay? Now, to be clear, until now, we were talking theory. This is not theory anymore. We're going to see deployment problems get solved through a conversational interface that understands both what developers need and what your infrastructure allows. So let me start by creating a new app. I will use .ai MCP through Cloud Code to see how this conversational deployment process actually works in practice. So let's do it. I will type my first command to create an app using the .ai MCP. Now, that MCP immediately recognized that my initial intent was too vague. Instead of making assumptions, it asks for more specific details, and it provides somehow helpful examples of different application types. That can be web application, databases, microservices, and front-end applications, right? It can be anything you want. That response over there shows how the system guides developers through the decision-making process rather than forcing them to know all the deployment options up front. It realized that my request was too short to deduce what I actually wanted, so it's asking me for more detailed intent. So I will respond with a clearer request for a stateless Golang application. Now, with this slightly more specific request, the system continues to guide me through the process. This iterative refinement is exactly how real conversations work between developers and platform engineers. But now it's happening automatically with AI that understands both the developer's intent and the infrastructure constraints. Okay, now we can see .ai MCP in action. It is calling recommend tool with my intent to deploy a stateless Golang application. The system is about to use AI-powered recommendation to help me deploy, create, run, or set up applications in Kubernetes. And here's where magic happens. The system has analyzed my cluster, and is presenting me with 3 solutions, each of those with a confidence score. And take a look at that. Notice how it's not just offering generic solutions, but options specifically tailored to my infrastructure. Option 1 is a custom app CRD with 95% confidence score. It is designed for application deployments with automatic handling of deployment, service, and ingress, right? By the way, that's a crossplane composition that I created earlier. Option 2 is a standard Kubernetes deployment with an 85% score, and it is offering the core functionality for stateless applications. And option 3 is a full production deployment with 80% confidence, and it is providing complete auto-scaling and fine-grained control. That over there is that 3-way collaboration in action. Platform engineers built those capabilities. They kept low-level Kubernetes resources like deployment and service available, but also created higher-level abstractions like the app CRD using Crossplane. On the other hand, I expressed my intent as a developer wanting to deploy a stateless Golang application. And now the AI inside the MCP is evaluating my intent against what platform engineers made available in the cluster, proposing the solutions that best match my needs. The important part here is that AI isn't just discovering what's in a cluster, it's semi-intelligently matching developer intent with platform engineering capabilities. This is exactly the solution we discussed. Platform engineers provide the building blocks. Developers express their needs, and AI bridges the gap. What should I choose? I'll choose option 1, obviously, for its simplicity and high confidence score. Okay, so now the system is calling choose solution tool with specific solution ID I selected. It's about to retrieve the configuration questions needed for this particular deployment option. This step shows or demonstrates how the system tailors the configuration process to the chosen solution rather than asking generic questions. So now the AI is asking for the required configuration settings for my Golang application. You should notice how those aren't generic Kubernetes questions, but specific, practical details that any developer would understand, like application name, namespace, container image, and image tag. And you should also notice that this is intelligent questioning, right? The system knows what deployment option I chose, and it is asking only for the essential information needed to configure that specific solution. So I will provide the required details, and that would be app name as silly demo, namespace AI team, and the container image, whatever it is. And now the system is calling answer question tool again, but this time with my responses. And you should see how the agent client intelligently or semi-intelligently parsed my input, which contained both the image and the tag, and automatically split it into 2 separate fields because that specific resource assumes that there are 2 fields. The important part is that I did not need to specify which part was the name and namespace or image components. The client agent figured out what I meant from the context and structured the data appropriately. Now we move to the basic configuration questions like port, hostname, and ingress class. Those are still developer-friendly questions, and they do not require really deep Kubernetes knowledge. The system even shows me what's available in my cluster, like noting that Nginx is available as an ingress class. And me, as a developer using this, I have flexibility to provide those details or simply say, hey, skip the process to advanced configuration. In this case, I will provide the basic networking details like port is 8080, hostname is whatever it is, and ingress class Nginx. Why not? And then again, the system processes my answers in the basic stage, structuring them properly, like, hey, port, host, and and the workflow continues to the next configuration phase. And now we are getting there, I promise, we're almost there. Now we are reaching the advanced configuration stage with questions about automatic scaling, replica counts, and repository settings, right? Those are more complex Kubernetes concepts. but still presented somehow in an accessible way, right? Now for this demo, I will simply type, hey, skip, to proceed to the open configuration stage, showing how the system accommodates different levels of complexity based on developer needs. Finally, we reach the open configuration stage. That's the last one, at least when questions are concerned. And that's where I can specify any additional requirements in natural language, right? Until now, we had questions and answers. This is kind of open question. And the system provides some examples. Let's say that they're helpful, like, hey, you can specify security requirements or performance needs or infrastructure constraints or resource limits and so on and so forth, right? And this is where AI's natural language understanding really shines. Instead of needing to know specific Kubernetes configuration syntax, I can simply describe what I need, like, hey, make it scalable between 2 and 5 replicas. Go for it. And now comes the crucial step, right? It's generating the final Kubernetes manifest. The system is calling generate manifest tool in that MCP with a fully configured solution ID. And you should notice the important requirement. It can only generate manifests after completing all configuration stages, which is required, basic, advanced, and open. The reason for that is that I want to ensure that the AI has gathered all necessary information before creating the deployment resources. And I want to prevent incomplete or misconfigured deployments. And there we go. Perfect, right? Here's the generated manifest showing how the AI translated my conversational inputs into proper Kubernetes configuration. And you should notice that it's using the UpCRD because that's the solution I selected earlier, when it presented me with multiple solutions. We can also see that all my inputs are correctly reflected. There is kind is up, name is silly demo, namespace is A-team, the container image and tag, networking configuration, and most importantly, the scaling configuration with minimum 2 and maximum 5 replicas. That's based on my last open answer. And there we go. Manifest is saved to a temporary file, and the system is asking if I want to deploy this application to my Kubernetes cluster. Of course I want to do that, right? So yes, and that triggers actual deployment process to my Kubernetes cluster. And that means that the system is calling the deployment manifest tool to deploy the Kubernetes manifest from the generated solution. Great, right? The deployment completed successfully. The system provides a comprehensive summary showing that my stateless Golang application silly demo is now running in the A-team namespace with autoscaling enabled between 2 and 5 replicas. It is accessible at the hostname I specified. There we go. Now, more importantly, notice how the UpCRD automatically created all the underlying resources like deployment, service, and ingress. This is the platform engineering abstraction working exactly as intended. It is hiding the complexity from developers while still providing the full functionality. And now you might say, hey, how do we know that it works? Well, because I say so. And if that's not good enough, let me test the deployed application by sending a request to confirm that it is working properly. There we go. The curl command successfully reached the application and the hostname I specified, and it is returning the expected response. This is a silly demo. And that confirms that the entire deployment pipeline worked correctly, from my conversational intent to a fully functioning application accessible through the configured ingress. Now, that was the happy part. And that was the part when my requirements align with the available platform capabilities and the system works smoothly. But what happens when you need something that the selected solution cannot provide? Let's explore how the system handles requirements that push beyond the boundaries of what's available. So let's test the system's boundaries. I'll create another stateless application, but this time I will explicitly mention ingress in my intent to see how that affects the available solutions. You should notice the difference this time, right? Because I explicitly mentioned ingress in my intent, the system now includes ingress configuration in the low-level Kubernetes deployment solution. And that demonstrates how the AI adapts available solutions based on your specific requirements. Now, for the purpose of the demo, I will choose the app solution again, because I want to test something special. I want to test what happens when I request something that it cannot provide. So let's go through the configuration stages quickly. We'll do similar answers like before. And now comes the crucial test. In the open configuration stage, I will request persistent storage. And why am I doing that? Well, I'm doing that because I know that the app CRD that I selected does not support storage attachment, right? I never set storage in the intent. Now I'm changing my mind, and let's see what happens. And here's the key behavior. Instead of hallucinating or generating invalid manifests, the system properly recognizes that the selected app solution cannot fulfill my storage requirements. It aborts the process and it asks me to start over. It is even suggesting that I can choose a different solution that can handle persistent storage. And that over there is exactly the right behavior. The system maintains integrity by refusing to generate configurations that won't work, rather than creating broken deployments. So we've seen what happens when we ask for a solution to do something it cannot. But let's see what if our intent itself doesn't fit the higher level abstractions. We'll test what happens when we need something more complex than what the higher level abstractions can provide. This time I will request a stateful application with persistent storage. You should notice something important here. When I specify persistent storage in my intent, the system's recommendations changed dramatically. The app solution that we were seeing before, the one that was previously ranked as 95% confidence, has now dropped significantly because it does not support persistent storage. It does not match my intent. And that over there demonstrates the key insight. App ranking adapts based on intent. The system, not intelligently, it evaluates which solutions can actually fulfill your requests. In cases where a solution fundamentally cannot meet your needs, it might not even appear in the recommendations. And here's the second key insight. Questions are dynamically generated. The MCP doesn't ask generic questions. Instead, it generates questions specific to both the solution you chose and the intent you expressed. And that ensures that you're only asked for information that's relevant to your specific deployment scenario. And now comes the third important insight about system flexibility. Instead of continuing with the standard MCP deployment process, you can circumvent it entirely. For example, by asking the client agent to save the manifest to a file instead of deploying it. And there we go. The system successfully generated a complete stateful set configuration with persistent storage through volume claim templates along with the service and ingress. And that demonstrates how the AI can work with lower level Kubernetes resources when higher level abstractions aren't sufficient, at least not for for stateful applications in this case. Okay, now that we've seen .ai in action, let's explore the underlying design philosophy and discuss what improvements would be needed to make this a production-ready platform engineering solution. Let's do it. The DevOps AI Toolkit, or .ai, is a direct implementation of the concepts we discussed at the beginning. It combines AI knowledge with platform engineering constraints to help developers deploy applications to Kubernetes without needing deep infrastructure expertise. This isn't just theoretical anymore. It is a working system that demonstrates how AI can bridge the gap between what developers need and what platform engineers can provide. The architecture is simple. The client agent, Cloud Code or Cursor or whatever you're using, remains generic agent that can handle anything. While .ai MCP focus specifically on converting user intents into reality by combining available resources in a Kubernetes cluster. While the MCP can effectively act as a standalone agent, it works better when connected to a more generic one. The MCP protocol proves superior to agent and other protocols for this type of specialized integration. Instead of platform engineers building rigid internal developer platforms that assume what developers need, .ai lets developers express their intent and uses AI to figure out the optimal deployment strategy based on what's actually available in their cluster. This fundamentally changes the relationship between developers and infrastructure from a rigid, predefined interface to a flexible, conversational one. The tool works by first discovering what's available in your Kubernetes cluster. which operators are installed, what CRDs are available, what storage classes exist, what ingress controllers are running, and much more. Anything, essentially. This discovery process captures the capabilities that platform engineers have set up and which AI doesn't inherently know about. It's this discovery phase that makes the system intelligent about your specific environment rather than just providing generic Kubernetes advice. Once it understands your Kubernetes capabilities, .ai uses AI to recommend the optimal deployment strategy for your specific application and environment. The AI has the general Kubernetes knowledge, but now it also knows your specific cluster configuration. This combination of universal knowledge and local context is what makes the recommendations both technically sound and practically applicable. The implementation provides two interfaces: CLI, which we haven't seen today, and then MCP, which we did explore in this video. Both are functionally the same, and both combine code for predictable operations with an AI agent for parts of the flow that are unpredictable. This optimization avoids involving AI for repeatable operations, which would only slow things down and increase costs. Now, to be clear, currently at this moment, .ai is a proof of concept that demonstrates that the core idea works, but it's missing several production-ready features. There is no observability for monitoring deployment process and success rates. It lacks policies and governance for enforcing security requirements and compliance. Lifecycle management or operations like updates, rollbacks, and scaling aren't handled. The system doesn't learn from successful deployments to improve future recommendations. There is no caching of previous recommendations or cluster discovery results, and it only supports basic applications, not databases, not clusters, not networking, storage, and other resource types that production environments actually require. So, it's very early. It's just me playing around. But here's the question. Does this approach show promise for solving the platform engineering challenge we've been discussing? What do you think about the direction? Does it make sense investing more into this project? And finally, probably most important, would you like to help develop it further? At the very least, giving it a star on vfarsig.ai GitHub repo takes just a moment. So do it right now. Thank you for watching. See you in the next one. Cheers.